Good morning everyone, and welcome back to our channel with our programming tutorial for lathes and CNC machines. This is the moment when our tutorial should change its name, because let's say in these days I've covered everything related to the mere programming of a lathe. We're talking about 2 axes, and I haven't really touched on anything related to powered tools because I want to focus on turning. So fixed tool, rotating workpiece. We've learned to move in the Cartesian axis, doing it in linear, circular, and angular ways. We've learned to use fixed cycles, so emptying a profile, threading, making grooves in sequence, tapping. We've learned to use variables and conditional and unconditional jumps. Now, with a bit of practice, all these videos we've made and watched together, and that many of you have actively commented on, some even pushing me to review 2 or 3 things and learn more, so you never stop learning. But by putting all these things together, we're already able, to tackle everything related to the movement in the tool space. But a lathe operator, a finished programmer, is not just point moving in space. He needs to start learning to manage the aspects of the machine tool. What other things do we mean? The gripping method, the problems we'll encounter during operation. A tool breaks, a tip breaks, a tap gets stuck because of the tailstock, the steady rest, the squaring of the machine, so the geometry of the machine, all those little things that make a programmer a lathe operator. Because a fully fledged lathe operator is 100, while a programmer is 20, and that's just 20% of your job. And I guarantee you that it's everything else that will make the difference, because if you can't get the program done, you can grab a book, call a supplier, or call a technician to do it for you. But when it comes to commissioning the machine and solving all the technical problems, it's you in front of the machine who has to solve it. So now, let's try to look at a set of possible issues, causes, things that can happen during your workday. There are obviously millions of problems, and we can't tackle them all. But let's try to look at a few. For example, let's talk about a very simple and straightforward program. I take a piece of material and I start drawing it wrong, right from the very start. I take a bar. This is my self-centering chuck mechanism. I give it a little cut. Okay, a cut with a diameter of approximately 90 and a length of 150 millimeter. It's a cantilevered bar set up so there's no tailstock or steady rest support. I go to measure this particular bar here, and I find that at the head section where I initially set my 0, the diameter is 90.02, and at the end section it's 90.25. .25, and yet in my program I only wrote X. X 90 and Z minus 150. Here I didn't repeat the X. So for example, how do I specifically solve this problem in this case? Of course, I put a compensation X at the end at 89.70 at 5, and I've solved my problem. But tomorrow, when I make another piece, I'll have the same problem, the same problem, the same problem. You just need to understand, it's really simple here. Identify the problem. The problem is in the head of the lathe. The heads of the lathe. Normally, if I have my bench here, this is the Z-axis, this is the cross slide, maybe tilted at a 45-degree angle. There's a bolted box. Check the self-centering chuck. Use a dial indicator to find errors, adjust the head, and confirm with a cylindrical turn. It's obvious that if over time my machine has taken some hits in this direction, broken some tools, or been stressed, not all of us are lucky enough to work on machines that just came out of the factory. There are also those who work on machines that are 10, 20, or even 30 years old. If you've seen a video I recently uploaded, that's a Mauro Graziano from '89, and yet it still works great. But every now and then, the squareness of the machine needs to be checked. In this case, if we go back to the overhang and we have some taper, this head will definitely be like this or that. Usually the heads drop like this because they take hits in this direction, but it's not guaranteed. We need to see if we're working internally, what needs to be done at this point. So, the very first thing is to place a dial indicator on the self-centering chuck, with the tip of the indicator on the chuck and the indicator locked on the turret. I move back and forth along the entire length of the self-centering chuck to check how much error I get. I loosen these 4 screws here. Usually there are adjustment nuts, and I adjust my head so that when I slide back and forth in the Z direction with the indicator resting on the self-centering chuck, the error is as close to 0 as possible. I tighten my 4 screws, perform a cylindrical turning, and check the error. At this point, if I have any error, it will be a bit more difficult, and I can adjust based on the error I get. I tighten my 4 screws, do a cylindrical turning, and check the error. At this point, if I have any error, it will be a bit more difficult. And I can adjust based on the error I get. There are also some pins that they would need very, very precise terminals turned. Normally, a self-centering tool has a thickness of 100-150 meters. This is more than enough to level the head. Okay, if you can't do it, don't keep going endlessly. Call technical support and have them do it. They are required to do it every time they put a machine into service. Usually there's an error of, I remember, about 2/100ths every 200 millimeters. Assuming every manufacturer has its own maximum error for overhanging turning. But if you go back 200 millimeters and have an error, know that the error is to be found in the head. We have a perfect head because we need to know it. This is an extremely complex and highly intricate machine. We have a perfect head, a self-centering chuck, usual jaws, and need to turn a 600 millimeter long, 90 millimeter diameter tube. We'll create a similar program, approach the tailstock and measure the piece centered outside the machine. Here we have 90 and 90.4. We've done our cylindrical turning program. Our head is perfect, verified by checking the self-centering chuck's outer diameter. This isn't technically correct, but is a quick explanation. We need to turn the piece to ensure it's cylindrical, using the self-centering chuck as a reference. We've turned between the centers, spindle, and tailstock, and found the piece near the tailstock is oversized by 0.4. Approach the tailstock and measure the piece. We have 90 here, 90.4 there. Usual turning done. Verify with chuck diameter. Not technically correct, but quick explanation. Ensure cylindrical using chuck as reference. Found piece oversized by 0.4 near tailstock. Tailstock low by 0. And here, 90.4. And yet we have done our usual We have done our usual program in cylindrical turning. Well, in this case, obviously, as I told you at this point, we already know that our head is perfect. However, we eventually verify it by checking the external diameter of the self-centering. This thing of the external diameter of the self-centering is not a didactically correct thing, but a quick thing. For what I explained to you, it is obvious that you have to turn the piece to be sure that it is cylindrical. However, the self-centering is our point of reference. Let's use it. Well, we have returned between the points, let's say between the spindle and the tailstock a piece. We have done a cylindrical turning and we have found that near the tailstock the piece is increased by 4/10. In this case we have a tailstock. That is low by 0. So I can never remember if it's double or half of approximately half or so. What does this mean? This is the spindle axis. This is the tailstock axis. And between here and here there are 2/10 more, which added radially will create a 90.4, not 0.2. What do? We need to raise our tailstock. How do we do that? First we pull back the quill and place our dial indicator here, which needs to be secured. The magnet under our tailstock is made like this. Normally, the body of the tailstock has 4 screws and an adjustment screw. The position of the adjustment screw depends on the type of machine we have. All we need to do here is loosen these 4 screws and use the adjustment screw to move the needle by 2/10. Be careful before going back to pushing. Make sure to close everything up and redo the operation. It's not simple here. We can't use our self-centering chuck to check if we have 90 and 90. It often happens that we have to do this multiple times. Of course, you might not do this with a scrap piece, but checking the tailstocks is important. If you use the tailstock a lot, you should check it every 2 to 3 months, because tailstocks are often used under very high pressures for safety reasons. So, over time, they might rise or fall, or they might get knocked around. That said, when you're working, you'll notice right away. Even if you're not necessarily turning a pin, you'll realize if you set a program and it doesn't hold the dimensions. For example, if you set 90 and it comes out 90.4, or whatever you program here, doesn't match what you program there, you probably have a tailstock that needs adjusting. Once you're done working with the tailstock, you move on and start thinking about drilling a nice hole with a cannon drill and then boring inside. What you need now is a steady rest. If you've never seen a steady rest, check out the website of Autoblock, Morari, or SMV, now SMV Autoblock, and look for hydraulic self-centering steady rests. They're very commonly used. They have 3 arms that, I must say, sorry, but I draw really poorly, have 3 bearings at the ends, and when they close, they are always concentric with each other, allowing the pieces to be worked on. Overhang. The tailstock is the same as the counterpoint. I always need to have the spindle's rotation axis perfectly aligned with the tailstock's rotation axis. What's the price to pay? The most dangerous thing is that the counterpoint pushes the piece. It will never be pulled out of the clamps, while the tailstock doesn't push. If I spin at high speed and have a slightly precarious clamp lock, be careful because the piece can get pushed out, posing a danger to both the machine and the operator if the machine isn't perfectly compliant with CE standards.
And be very careful, because this kind of thing often happens in situations like this.
The issue of not having the tailstock aligned with the self-centering device, in quotes, is secondary for your safety, but not secondary for your workpiece. Obviously, when you turn, you'll have the same problem on the outside, meaning you'll have a cylindrical turning, depending on whether the tailstock is too high or too low. It will be wider at the top or at the bottom. What should be done? Now, there are two essentially similar ways to center the bezel. If you can turn the piece as before between centers, it's very simple. But if not, you do it in a cantilevered position with a short piece, with the tailstock in. This position, tailstock open. Turning the piece between centers or in a cantilevered position, but with a piece securely locked and sized appropriately for the dimensions of the tailstock. The tailstock has a square body. This is the tailstock, seen from the front. This is my piece, and this is the tailstock. The tailstock is secured to the guides with a plate and 4 screws, and usually 3 adjustment screws, okay? So, turn the piece even manually. We don't care about the turning dimension. What's important is that it's turned in the contact area of the tailstock arms, which will be open. Stop the machine, clean up all the residual chips completely, because if chips get stuck between the tailstock and the support plate, the tailstock will never center properly. So, turn the piece even manually. We don't care about the turning dimension. What's important is that it's turned in the contact area of the tailstock arms, which will be open. Stop the machine and clean up all the residual chips completely, because if chips get stuck between the tailstock and the support plate, the tailstock will never center properly. Once you've cleaned everything, screw these 4 screws. Loosen the 3 adjustment screws by at least 5 to 6 m and carefully close the tailstock. As you close the tailstock, you'll see it gently lift because it will have dropped at that point. Then, securely tighten the 4 screws in a crisscross pattern, 1, 2, 3, 4. First by hand, then a bit tighter. If you have a torque wrench, you're my heroes. If you don't, use a pipe, no longer than 40 centimeters, and tighten it pretty firmly, with care and precision. Once you've tightened the 4 screws with the tailstock closed, bring the 3 adjustment screws against the tailstock. Yes, more than adjustment screws, they are mechanical stops. At this point, your tailstock is centered and your turning operations will be at least more precise. Of course, the centering, the quality of the tailstock centering, also depends on the quality of the guides to which the tailstock is attached. What does that mean? If you have a very old and battered 2-meter camera, a bezel centered here might not be centered here. Yes, because some bezels move. There are bezels with controlled axis. There are bezels that attach to the carriage. There are bezels that move manually and are fixed. Well, these are the first problems you might encounter. Some of the issues, because the first ones depend on what kind of machining you do. These are some of the mechanical problems you might face in your life as CNC lathe programmers and setup technicians. These aren't things that are usually explained in a course. They are things you should see in a machine shop. Since I can't have you all in a machine shop, I hope to have presented you with some possible solutions for the tapering issues in your parts that inexplicably turn out different from what you programmed. It's just a drop in the ocean. In the next videos, we'll look at other small problems that can occur when you're facing a lathe thank you for being with me, and I look forward to seeing you next time. Have a great day.